Now it is your turn. Let's build and stress this chapter's trie operations in C and remember to free everything you allocate. For Lab 1, you build a trie for lowercase words with insert and search. You start from the trie node struct, an array of 26 child pointers plus and is word flag. Implement 3 functions. The first is trie insert. It adds a word to the trie. The second is trie search. It returns whether a word is stored. The third is trie free. It releases every node when you are done. To test, insert bat, ball, bad, and cat. Then search bat, which is found. Search BA, which is absent because you never inserted it as its own word. Search ball, found, and search cats, absent. One tip: your new node helper must zero every slot of the child array before it returns. An uninitialized array reads as 26 real children, and that breaks everything. Take a few minutes and try this yourself before the solution. Let's look at the solution. Trie insert comes first. It starts at the root and walks the word one character at a time. For each character, it checks cur arrow child at index ix. If that child is null, the path does not exist yet. So it creates a fresh node with new node and links it in. This is how the trie grows. Then it steps down into that child and moves on to the next character. When the word is finished, it sets cur arrow is word to 1. That flag is what marks the end of a real word. Now the search half of the lab. Trie search takes the root in a word and returns 1 or 0. It walks the word one character at a time. If the child for that character is missing, the path breaks, so the word is absent and we return 0. Otherwise we step down and keep going. And here is the line that matters most. We return cur arrow is word, not 1. Reaching the end of the path is not enough. Look at the output for proof. Searching for B, a returns absent even though bat and ball both pass through that node. And cats returns absent too because the path runs out. Cat was stored but nothing continues past the T. For lab 2, you extend your trie with a prefix query. Write a function called trie starts with. It returns 1 if any stored word begins with a given prefix and 0 otherwise. You can reuse the insert from lab 1. To test, insert star, start, stop, and stack. Then query sta, which is yes. Query st also yes. Query stac yes. And query stz, which is no because no word takes that turn. The key idea is simple. Walk the exact same character loop as trie search. The only difference is what you return at the end. Try tracing by hand where stz fails before you write any code, then give it a go. Let's look at the solution. Trie starts with looks almost exactly like trie search. It starts at the root and walks the prefix one character at a time. If a child along the way is null, the prefix path breaks, so it returns 0. No word can begin this way. But when it reaches the end of the prefix, it just returns 1. Notice it does not check the isWord flag. We only care that the path exists, not that a word ends here. That one change is the whole difference from search. The output matches our hand trace. ST, ST, and STC are all yes. Only STZ is no, because no word ever turns down the Z branch. Lab 3 is the challenge. Count how many stored words share a given prefix. This is where the trie's sharing really pays off. Write a function called trie count prefix. First, walk to the prefixes node just like starts with does. Then count every node below it that has its word flag set, including the prefix node itself if it is also a word. A tip: split the problem in two. One part is the walk that finds the prefix's node. The other part is a separate recursive helper that counts the word nodes in a subtree. That helper has the same shape as the size and count leaves recursion from Chapter 9. Take about 30 minutes and try it. Lab 3 needs two pieces. Here is the first, a helper that counts every word in one subtree. The base case: a null node holds no words, so return 0. This node itself contributes 1 if its word flag is set, and 0 otherwise. Then we loop over all 26 children and add each child's count into the total. Notice we call the helper on every slot, including the null ones. The base case handles them, so there is no extra test here. Then we return the total. This is the part whose cost is proportional to the subtree, not to the prefix length. And here is the second piece. Walk to the prefix, then hand off to the counter. We walk the prefix one character at a time, exactly like starts with. If the path breaks, no word starts this way, so we return 0. And when the prefix is used up, we count every word in the subtree below where we landed. Look at the numbers. The prefix COD covers 4 words. The shorter prefix CO covers 5, because it sits higher up and its subtree is bigger. And X, Y covers 0. The path breaks on the very first character, so the walk returns before any counting happens. That wraps up tries. Nice work, and I will see you in the next chapter.